All right, let's take a look at the composition of functions. Now, definition of f composed with g. First of all, as far as notation goes, we notice we have this f circle g. That's a little circle. It's not the letter O. It's not the number 0. It's read f of g, or the function f composed of g. And what it means is that we're going to take g of x and plug that into f of x. Now, I like this little illustration of the idea of a function machine, that you can think about a function as being this crazy little machine that, if, for instance, if we have g of x, g is our function, and what we'll do is we'll take all these x's and throw them into the function machine, and g of x is going to do all of its work, and what it's going to spit out is g of x. Now, when we're taking the composition of functions, what we're doing is kind of creating this chain of two function machines in a row. And the first function machine is g, and we're going to take x and plug it into g first, get out g of x. Then I'm going to take g of x and plug it into my new function f. And what we'll get out is f of g of x. So I can't really reiterate this enough, that we take x and first plug it into g and then plug it into f. So let's consider f of x being x squared plus 2 and g of x being 3x plus 1. And we really want to think about this as being f of that g of x. And so within function f, I'm going to plug in 3x plus 1. So going back to f of x is x squared plus 2. But instead of x, I'm going to plug in that 3x plus 1 instead. Then, when we start to expand it all out, 3x plus 1 squared is going to be the 9x squared plus 6x plus 1. And then to that, I'm going to add 2, and then we'll get our final answer of 9x squared plus 6x plus 3. If we were to think about domains, going back to the beginning, the domain of f is going to be all real numbers, because we can square anything. And the domain of g, well, that's a linear function, so that's also all real numbers. So nothing really too interesting here, that our domain of f of g is also going to be all real numbers. Let's try another similarly quick example, that if we want f of g when f is x to the fourth and g of x is x squared plus 5, remember that we're finding f of g of x, and our g of x is x squared plus 5. So in my function f, which was x to the fourth power, we're just going to take x squared plus 5 and plug it in there. Now, as far as your homework or anything like that goes, if you leave it as x squared plus 5 to the fourth, I'm perfectly fine with that. I'm not going to expect you to expand that at all. Going back to domains, again, when it came to the domain of f, well, that's x to the fourth. Its domain is going to be all real numbers. And the domain of g, because we're squaring it, again, is all real numbers. So nothing interesting here. The domain of f of g will also be all real numbers. Now let's take a look when f and g don't have domains that are all real numbers. For f, it is, because we're dealing with x squared, we can square anything, and that domain is going to be all real numbers. But when it comes to the domain of g, see, we're dealing with the radical function, a square root, and we need to make sure that x squared minus 4 is greater than or equal to 0, because we don't want to take the square root of anything negative. Please, when you try to solve a quadratic inequality, you have to factor it, and everybody's usually good at that, x plus 2, x minus 2. But use a sign chart. This will give us two critical numbers, one at -2 and one at +2. Both of these will make the thing equal to 0. Neither of them will make it greater than 0. What we have to do is test each interval. And on the interval from -2 down, if we picked any value there, like -20, and plugged it in, -20 plus 2 is negative. and negative 20 minus 2 is negative, so I'll have a negative factor times a negative factor, making everything on this interval positive. If we pick something in the middle, like 0, x plus 2 becomes positive, whereas x minus 2 stays negative, so that product will be negative. Then picking something extraordinarily large, like a billion plus 2, and a billion minus 2 are both positives. Multiply them together, and it's positive. Looking at our sign chart, it now is easy to determine that. And looking at our sign chart, x squared minus 4 is going to be greater than 0 when x is less than or equal to negative 2 and greater than or equal to positive 2. Now let's actually compose the two functions. Since we're trying to find f of g, it's going to be f of g of x, and g of x was that square root, x squared minus 4. So I'm going to take that and plug it into the x squared plus 5. And when we simplify, the square root being squared, those two will cancel and leave us with x squared minus 4 plus 5. And simplifying is x squared plus 1. And again, it looks like, x squared plus 1, that's going to be having a domain of all real numbers. However, remember, this is not its own function. It's a composition of two separate functions. So when it comes to the domain of f of g, remember, we only could take x's and plug them into g first, which meant that we were limited in having a domain of x being less than negative 2 and greater than positive 2. Only those numbers could have been used in the first place. So you wouldn't ever have taken, say, x equals 0 and plugged it into g in the first place, so it's also not a part of the domain of f of g. Maybe I can explain the domain thing a little better like this, that when we're looking for the composition of f of g, remember I said that we're going to take an x, and the first function machine we're going to plug it into is the g function. So that what comes out is g of x. Then we're going to take that g of x and plug it into the next function, the f function. And what will come out will be f of g of x. Well, we can think about domain as maybe this bin of parts sitting off to the side. All of the numbers that we can possibly use. And for a lot of functions, this domain, this bin of parts, includes any number there is. And we can take a 0 and plug it in there. And we can take a negative number and fractions. And we can use any number we want to plug into our functions. However, sometimes we come across these special functions like g. And the parts bin for the domain of g is limited. I can't use all those numbers. The only ones that we said we could use were when x was less than or equal to negative 2 or greater than or equal to positive 2. All of these x's are going to come out of this bin, and that bin only includes these numbers. Now, since g is the starting off point of this entire chain of function machines, that's going to mean that the domain of our f of g, this composition of functions, it's going to be the same. That x is less than or equal to negative 2 or greater than or equal to positive 2. Let's look at this composition of functions with f being the square root of x and g being x squared minus 4. And there's going to be a lot of similarities here, but some things are a little different. When we check out domains, this time f of x has a limited domain. That's where our square root is, and what's underneath the radicand, has to be greater than or equal to 0. However, the domain for g this time is all real numbers. I'll let you maybe think about what that domain of f of g might be while we go through the composition of these two functions. So back on the left here, we're trying to find f of g of x, with g of x being x squared minus 4. So that's what I'm going to plug into the square root, is that x squared minus 4. So there's really, don't be fooled. Don't tell me this thing is x minus 2 or anything crazy like that. This thing doesn't simplify at all. it's just x squared minus 4. Now when we're thinking about the domain of f of g, we realize that it's probably not just going to be that x is greater than or equal to 0, or that x is all real numbers, because I have this radical function again, and I don't want my radicand to be negative. So we have to take a closer look at this x squared minus 4. We need that thing to be greater than or equal to 0. And we just saw that that happens when x is less than or equal to negative 2, or x is greater than or equal to positive 2. Let's take a look at domains again. Initially, when we're thinking about our bin of parts, the domain of G, in this case, right now, it's all real numbers. We can have positives, negatives, or anything, and we can throw it into function G, and that's just fine. Where the problem comes in is this transition. When we're thinking about the domain of f, its bin of parts, because it's a square root function, is only those numbers where x is greater than or equals 0, right? And I don't really want to think about it as x. It is an x, but it's not really an x, because the number that we're trying to pull out of this bin of parts isn't really x. It's the g of x. It's the range of x. It's what came out of g. That's what we want to make sure is in the domain of f. So we have to kind of check that. And that's what we were doing when we said g of x. We want to make sure that g of x is greater than or equal to 0. That was the x squared minus 4 being greater than or equal to 0. And how we figured that our domain is less than or equal to negative 2, greater than or equal to positive 2. How's this for a curveball? We'll keep the same two functions, but we'll reverse the order of composition. So that means that now we're going to try and find g of f of x. So we're going to take x and plug it into f first. And then I'm going to take that result and plug it into the x squared minus 4. So I'm going to take square root of x and plug it into x squared minus 4. Now when we simplify, square root of x squared leaves us with x, and our result is x minus 4. It looks like x minus 4 has a domain that's all real numbers, but of course we know better than that. Now we know that f of x being the square root of x, that means that x has to be greater than or equal to 0. But for g of x, it can be all real numbers. So our domain is already limited when we're talking about the domain of f of g, the composition, the entire system of function machines. But the domain here is already limited now by x being greater than or equal to 0, not the greater than negative, positive 2 and less than negative 2 part. What's going to come out of f is going to be a positive number, because it'll be the square root of something. That's part of the domain of g. So we don't have any other restrictions on our on the domain of our composition of two functions. Let's try just one more example. First of all, real quickly looking at the domain of f and the domain of g. F is linear, so its domain is all real numbers, and g is also linear, so its domain is all real numbers, which, oh, thank goodness, finally back to the good old all real numbers for the domain of f of g. So really, let's just take a look at the composition of functions in two different ways. Remember that with f of g, I'm going to take f and plug in that x over 3 minus 4/3. That means we'll do 3 times x over 3 minus 4/3. And add 4 to that. Distributing the 3 leaves us with x minus 4 plus 4, and a really nice result of just x. Practice going the other way now. G of f of x means we're going to go g of, and my f of x was 3x plus 4. That's going to get plugged into the function g, x over 3 minus 4/3. But my x is now 3x plus 4. So when we simplify, 3x over 3 is x, plus 4/3 and minus 4/3 leaves us with that same interesting result of just x.